Hello, good afternoon, good morning. My name is Chiara Benetti, and I welcome you on behalf of ETA Florence, technical organizer of IEA Bioenergy webinar series. Today's webinar is entitled Progress in Commercialization of Biojet Sustainable Aviation Fuels, Technologies and Policies. The webinar will be moderated by Jim McMillan, Emeritus Senior Engineer from the National Renewable Energy Laboratory. And the speakers will be Jack Saddle, Professor Emeritus, University of British Columbia, and Susan Van Dyck, Research Associate, University of British Columbia Independent Consultant. As usual, during the webinar, you have the possibility to drop questions by using the Q&A tab that you can find at the bottom of your screen. Our speakers will reply to your questions either by typing the answer in the Q&A tab or by answering live at the end of all presentations. Please do only use the Q&A tab for questions and do not use the chat box. As usual, the recording and the presentations of the webinar will be published tomorrow on IEA Bioenergy website. That's all from my side, so I'll give the floor to Jim and enjoy the webinar. Thank you. Bye-bye.
Thank you very much, Chiara, and welcome to the webinar, everyone. Good day, early day or late day, depending on where you are. It's my pleasure to moderate today's session. It's being brought to you by IEA Bioenergy Task 39. And Jack Sadler, who will speak first, will say more about that. But it's a pleasure to be here representing my IEA Bioenergy Task 39 colleagues. And I welcome you to the webinar. Again, post your questions in the Q&A. We will entertain clarifying questions to our ability during the presentation, but the major question and answer session will appear after both the speakers have presented. So without further ado, I'd like to introduce my Task 39 colleague, Jack Sadler, Distinguished Professor Emeritus at the University of British Columbia, who I've had the pleasure to lead Task 39 with for several years in the past, and he's going to start us today. So Jack, I'm going to turn it over to you.
Thanks, Jim. So first of all, thanks to everybody for joining us on this webinar. So I appreciate you making time for the call today. I want to thank Jim for agreeing to be the moderator, because I think any of you have worked with Dr. McMillan know that Jim is famous for asking insightful questions. I also want to thank Thomas Ekbom and Glaucia, the current task leaders at Task 39, because this is work that was approved by Task 39. What I'm going to do is set the scene in the next 5 minutes or so, because my colleague Susan Van Dyck is going to give by far the meat of the report. This is the website here. So on this slide here, which you'll get a copy of, is the Task 39 website. So the report is actually accessible on that site. Next slide, please, Susan. But what you'll see is that this report is actually built on a report that was done about 3.5 years ago. So if you look at it, we were fortunate again, Susan and I, to have Jim as the moderator. My colleague Jeff Thevet. In Canada, we have a CSAF. So CSAF is the local group trying to decarbonize aviation. So we don't have Jeff on this talk. But again, I want to show you why, from a Canadian perspective, this report is very important. Next slide, please, Susan. So Susan and I had been working with Task 39. We also work with other agencies. On the top right here, you can see a report we did for IRENA a while ago. And also, these are the other IEA reports that you can access just now. We're very fortunate to work very closely with our US colleagues. My sense is the US is doing a lot in this area, which Susan will cover in a bit more detail. Next slide, please, Susan. The main area that Susan and I are working on is what we call BC Smart. This is the British Columbia sustainable marine aviation, rail and trucking. So we're really pivoted towards decarbonizing long distance transport. I think, as Susan will cover, aviation is a very good example, because I think biofuels or sustainable aviation fuel is pretty well the only way you can decarbonize long distance transport. Next slide, please, Susan. The reason why this is so important for us in Canada, got a couple of slides here that I'll show you. So this is really taken from carbon emissions. So if you look at 2023, that's the year we have most data for. We're still in the middle of 2024. You can see that fires, I mean, Jim didn't talk about it, but some of the issues just now in Florida, if you've been watching the news with regard to the storm. So we have these 1 in 100 events that are happening every couple of years now. Next slide, please, Susan. Why it's of concern for us in Canada, if you look at this slide here, the 2023 wildfire estimate was actually more than everything else added together. So if you look at Canada's total in 2021, so we were basically about 4 times more from forest fires. So we have a big concern in Canada with climate change, with what's going on, and that's why the work that we do in BC Smart, it will be ongoing. Next slide, please, Susan. Again, I think what Susan will cover is the policy environment. We're fortunate in British Columbia to have a carbon tax. We have a low carbon fuel standard. So we have the right policy environment where we're really trying very hard to decarbonize. We're also lucky to be working closely with a local oil refinery who's also trying to decarbonize. Again, if you access the Clean BC roadmap, you'll see what policies are being used. Next slide, please, Susan. And then these are some of the reports that we've done with BC Smart. This is the website here. We've looked at co-processing, decarbonizing rail, decarbonizing marine. So all of this information is accessible publicly. Next slide, please, Susan. So we've been at this for a while. We're very fortunate to get support from Boeing. So Boeing funded us about actually 6-7 years ago to look at the feasibility of going from forest residues to jet fuel. Susan played a key role in pulling that report together. Again, this information is available on the Task 39 website. So if you want to look at the study, there is a substantial reduction in carbon emissions if we use forest residues. Next slide, please, Susan. Again, I won't go through this in detail because Susan will cover this in her presentation. So the Task 39 report, I think, has quite a few take-home messages that will be covered in detail here. Next slide, Susan. So really, what will hopefully you'll get in the next 30 to 40 minutes is that we estimate that probably Biojet SAF will always be more expensive than fossil fuels. So you need some sort of policy incentive. Enabling policies will be critical, and Task 39 is covering quite a lot of that work. I mentioned in BC, we have the low carbon fuel standard, we have a carbon tax. One of the issues is that there's ongoing competition for lipid feedstocks because the same feedstocks are used to make diesel, renewable diesel. So competition, and also virgin lipids we mostly use for food and for cosmetics. So the full report that we're going to be talking about is available on this website here at the bottom. And so lastly, I want to thank my colleague Susan Van Dyke, who did all the heavy lifting on this report. My last slide, I think, Susan, is the next one. So again, if you look at more information, I know Susan was at the meeting in Houston a couple of weeks ago where there was a lot of information covered. I was at a meeting in Seattle earlier on this week, which is looking at forming a cluster. So it's a very interesting area, a lot of changes going on, and that's why I think the report will be of value, because a lot has happened in the last 3 years, but a lot more has got to happen in the future. So with that, I want to hand over to my colleague Susan Van Dyke, who's going to go into much more detail about what's covered in the report. Thanks a lot, Susan.
Thanks, Jack, and thanks to everyone that are attending today. So, as Jack mentioned, you can download the report from the Task 39 website. There's a lot of topics covered, so I've just selected a number of key areas, and I would encourage you to download the report if you're interested in further information. Because now it's not working. So just to set the scene, we all know that SAF is going to be the most critical component to decarbonize aviation. For a net zero target, the estimates are generally that SAF must deliver about 65% of emission reductions, and the estimated volume of SAF needed by 2050, depending on the reports, but over 400 billion liters is kind of estimated. Current production is still less than 1%, I think. Last year was only about 0.5%. And there has been quite a lot of progress. So we've got 11 pathways approved under ASTM. But I think what people don't forget sometimes is that ASTM approval does not mean that a technology is commercial or that the fuel produced will be sustainable. ASTM is only concerned with the safety aspects. So some of the technologies were approved already as far back as 2008, 2009, and that is still not commercial. There are also many new pathways under evaluation, and these are ongoing. So if you look on the ICAO website, you'll see they've got a SAF tracker that tells you that about 337 facilities have been announced, are under construction or in operation. 127 airports have distributed SAF, and that there's 53 billion liters under offtake agreements. But so this makes it sound really fantastic. But what we have to bear in mind is that a lot of those facilities might never happen. And the 53 billion liters under offtake agreements, that's not sold. It's merely, in most cases, this is just like a memorandum of understanding. And some of these companies that sign offtake agreements, the main reason for it is really to obtain funding. So when we look at what do we expect, how fast technologies are going to become commercial, and how quickly will we see production expansion, we know that HEFA is still the only fully commercial technology, and it's generally agreed that by 2030 the majority of SAF will come from HEFA. But then what the general consensus is that other limited volumes of waste fats and oils will by then impact further growth, and other technologies will be expected to deliver these volumes. And yes, we need other technologies to reach commercial scale, but this has been challenging. And everybody and every report wants to see a graph like this that shows you when exactly are we going to see this technology producing how much, etc., etc. And as we see, there are hundreds of projects that have been announced, but the question is how many will succeed. And depending on who you talk to, pessimistically, maybe 25%, optimistic, maybe 50%, but not all these companies will succeed. That's just the reality. And there's also, I think, a lot of unrealistic expectations about how fast these technologies will become commercial. So commercializing a new technology takes time. What we see is just moving from one technology readiness level to the next. Even if everything goes well, it can be 2 to 3 years per stage of TRL. So if a company is only at the pilot scale, that should tell you realistically that it's going to be years before they reach a commercial scale, regardless of what they try to tell you. It will take time. Then even when a company has been announced, they have to get funding, permitting requirements, construction, and even after construction is completed, the commissioning could still take up to a year before a facility is running at capacity. And some technologies, such as gasification, where there's a huge amount of infrastructure, have very long construction periods, even after the final investment decision. So 5 years seems to be an average time for construction of these facilities. And then we also have to distinguish between announcements versus final investment decision stage. So we only can only really start considering volumes, potential volumes, I think, when a company is at FID stage. Because SAF projects based on unproven technologies represent a high risk for investors. And a lot of investors and bankers will tell you at these conferences, they're waiting for these new technologies. They're waiting for the first one to succeed before they're preparing to invest. And there's always a huge danger of scaling up too fast. And within the biofuel industry, we've seen this happen. There's a lot of pressure on companies, and you see some of these announcements, an unproven technology, and they are already saying they're going to build a facility with 200, 400 million liters per year. And the reality is that that might be too fast to scale up. There are even people saying that, for example, the Fulcrum Bioenergy facility that just closed down, they had a 40 million liter capacity, and some people in the field are saying, well, they thought it was maybe scaling up too fast. So we have to be realistic. Things are going to take slower than we think. And the reality is that the targets are so ambitious that meeting these SAF targets will be extremely challenging. And some of the conferences that I've been attending recently, definitely the message are that we are unlikely to achieve the 2030 targets at this stage for both the EU and in the US. And that's not just pessimism, that's also just being realistic about how long these things take. And although this report mainly focuses on technologies and policy, what I realize some of the most overlooked challenges is feedstocks and supply chains. So while we focus on the technology, there are critical issues that we are forgetting. So we need to establish cost-effective feedstock supply chains, especially for feedstocks such as agricultural residues and forest residues, because these supply chains don't exist. When we talk about crops, yes, we have supply chains. Then the other thing is to distinguish between the low energy density feedstocks, such as forest and agricultural residues, which cannot be transported economically over long distances. And in those cases, the location of the biorefinery must be close to the feedstock, but this may not be close to the downstream fuel supply chain. So they are already starting to look at that and realizing this is a problem because we have our current fuel supply chains downstream for getting fuel to airports, but we're going to have to develop a whole new supply chain for SAF that we haven't got yet. Another issue that I want to talk about is this whole issue of announcing volumes of SAF for a facility. So all technologies, like 95%, produce multiple fuel products with different ratios of SAF. So we can't really speak about SAF biorefineries as much as we want to. And some companies say that they're going to produce SAF because this is sort of the buzzword. But so this graph shows you the distribution of products. So the red being jet, the yellow renewable diesel, and the blue light ends such as naphtha, which can be converted into gasoline. So there's a big difference, and this just shows a few of the technologies. So the capacity of a SAF facility is actually not all jet fuel. And what we see, and I'm going to talk about this a little bit more, you can either have a small volume of jet or you can have a large volume of jet. And that can be done for any technology. You can increase the SAF fraction, but you need to do additional processing, and that comes at additional cost. A general rule is the more steps you add, the more expensive the process becomes. And there's a lot of misconceptions that leads to overestimation of SAF. A lot of the volumes that are estimated look, for example, takes HEFA and says 50% for all facility, or takes gasification Fischer-Tropsch and says even 70% SAF. But as I will explain, refineries choose the product slate depending on the economics. So only if the economics make sense will refineries choose to produce a bigger fraction of SAF or even produce SAF at all. So HEFA, the hydrotreatment of oils and fats, is fully commercial, but this is commercial for renewable diesel production. Production of SAF using this technology is only done at a limited scale. So while we can divert a jet fraction from the existing capacity of these facilities, this can help us to provide a substantial SAF volume in a very short period of time. So I'll explain on the next slide that we can produce 15% SAF from total biorefinery capacity for HEFA facilities, and under circumstances that are favorable, we can produce 50% or more of this capacity. And if you look at some of the estimations for HEFA capacity, this might go like 30 billion liters by 2030. But the problem is actually getting refineries to divert a fraction of their products to SAF, because this is a critical issue. Oils and fats chemistry favor the production of renewable diesel. The average chain length of a fatty acid is 18 carbons, whereas the carbon number for jet fuel is here between C8 and C16. That's the light green here. So after hydrotreatment of our fatty acids, most of these fatty acids are still in the diesel range. And note also that the diesel range overlaps with the jet fuel range. So a refinery doesn't have to produce jet. The whole fraction can go into the diesel. So when a refinery is being built, the refiner decides, am I going to build renewable diesel, or am I going to just make am I going to make diesel and SAF? And if it wants to make SAF, it has to add additional infrastructure and additional processing. So just from a pure hydrotreatment step, there's a little bit of cracking that takes place. So we will have about 15% of our fatty acids, hydrotreated fatty acids, will fall into the jet range. So without putting in additional hydrocracking, just based on hydrotreatment, a HEFA biorefinery can produce about 15% SAF, but they have to then put in additional distillation column to separate out that 15%. So there is some investment required. But a HEFA refinery can also produce more than 50% SAF fraction. So when we just want to produce a 15% fraction, or more than a 15% fraction, the refinery will need to now have a separate hydrocracker, which breaks up the longer chain molecules into shorter chain molecules. Then they also need to add fractionation, and they also need to use more hydrogen for processing. So this becomes more expensive. And on top of that, additional hydrocracking to get more than 50% will also reduce your liquid yield by 10%. So not only do you have a bigger investment and it's more expensive, you also have a lower yield of your valuable liquid hydrocarbon products. So SAF production from HEFA biorefineries is not favorable economically unless there are additional policy drivers. So this can be in the form of bigger incentives. And I'll mention later that this is what we see in the Inflation Reduction Act, but also in the EU, for example, because there are penalties for not delivering the SAF. This might be a policy driver, a stick. policy to drive the production of SAF from these refineries. And a separate issue really is the fact that road transportation and aviation wants to use the same feedstocks for both. So you can produce biodiesel, or you can produce renewable diesel, or you can produce SAF. But the problem is that the way that policies are structured is that it favors the production of road transportation fuels. So we've already clarified that it's more expensive to produce SAF. Now we're also saying that renewable diesel gets more incentives. So under the US Renewable Fuel Standard, for example, the calculation of the renewable identification number, which is really the incentive, is based on energy content. So under this policy, SAF can generate 1.6 RINs per gallon, while renewable diesel earns 1.7 RINs per gallon. So that's got a direct economic impact. So if you just look at that policy, SAF cannot compete directly. So the policy must actually favor the production of SAF if you want to see these HEFA refineries shifting to even a small SAF fraction. And the reason why we are saying that it should be shifted to aviation is because aviation does not have another option, while road transport has many options, including, for example, electrification. And the IRA currently has a higher incentive for SAF compared to diesel. The other thing when it comes to HEFA is that everybody's saying oils and fats feedstocks are limited. So but the issue here is that there's more a focus on waste feedstocks. So I think there's sort of a general consensus that the volumes of waste feedstocks are kind of static, and we'll see about 30 to 40 million tons of waste feedstocks. And if you look at that, you can supply about 10% of SAF demand from that. Then we have a lot of crop-based oils, about 220 million tons. But of course, the sustainability and the competition with food is an issue. And although millions of tons are certified as sustainable under organizations such as ISCC, this is an issue. So crops are banned for production of SAF in the EU, but it's not banned under CORSIA. And what we will see is in many parts of the world, these crops will be used to produce SAF. And could potentially give substantial emission reductions. But what I want to just focus on here is these emerging feedstocks, and I want to divide it into two groups. So these are feedstocks that are not commercially available, but has substantial potential. Intermediate or cover crops are non-edible oilseed crops such as Carinata, Camelina, pennycress, and so on. So the World Economic Forum Clean Skies for Tomorrow report estimates that there's a potential for about 70 million tons of oils from these intermediate and cover crops. And then we also get perennials such as Tritopha and other types of oil seeds, and they estimate that there's potential for 85 million tons. And of course, these can be grown on marginal land, etc. So these can achieve low carbon intensity, but these crops are not commercial. However, what I want to leave you with this sort of conclusion is HEFA is fully commercial. While we can say, okay, let's stick to waste and oils and ignore the rest, we will then only get 10%. But if we can focus on actually developing some of these other crops to expand the volumes of oils that are very sustainable with low carbon intensity, we can potentially expand SAF production based on an already commercial technology that is optimized and actually has a reasonable production cost. And this is actually what they are doing as part of the SAF Grand Challenge, to say, let's focus on establishing these crops, looking at some of the challenges. And if you've heard me speak about feedstocks or give a talk about feedstock, I focus a lot on what are the challenges and how can we overcome this. Then HEFA, as I see it, will supply the most of our SAF until 2030 at least. The second opportunity for SAF is really through co-processing, which is the insertion of bio-based intermediates into existing refinery processing units and the simultaneous transformation of these intermediates with petroleum distillates to produce lower carbon intensity fuels. So it's approved under ASTM 1655 for hydrotreated oils and fats, 24%, direct oils and fats 5%, and Fischer-Tropsch liquids 5%. And it's fully commercial for fats and oils, the 5%. Although this is the same feedstock that we're talking about for HEFA, and the process is essentially HEFA, this is a low-cost opportunity for actually expanding SAF volumes by inserting these bio-based intermediates. And when it comes to Fischer-Tropsch liquids, that was originally what Fulcrum was going to do. And there's even the opportunity for alcohol to jet oligomers to be inserted in a co-processing. So the technology is not unusual, but the low-cost opportunity is very significant. This just shows you some of the main insertion points that can be used and are being used currently by existing refineries. So co-processing can rapidly increase SAF volumes because you can use existing infrastructure. So refineries already have the permits available and they've got all the resources, they've got all the expertise. All it needs is a relatively low investment. For example, if you're just going to put a 5% oils and fats into your refinery, you need investment into, say, feedstock storage tanks, piping, and a couple of other things. But it's not a huge investment, and the refineries have all these funds available. Plus, you are now connecting into an established downstream supply chain for delivering of this low carbon intensity jet fuel. So this is a significant opportunity. And what we see, multiple refineries in the EU are already producing SAF this way. I think there's at least seven refineries. And this is driven by the ReFuelEU Aviation mandate, because there's pressure on the fuel supplier to blend SAF. This is an opportunity for them to produce an already blended SAF, if you can call it that. But in the US, what we see is that the Inflation Reduction Act doesn't allow for co-processing to earn incentives. Co-processing of oils and fats, co-processing of Fischer-Tropsch liquids can earn incentives. But because co-processing of fats and oils can't earn incentives, refineries in the US seem to just be producing renewable diesel. At the same time, refineries in the US and also in British Columbia are already co-processing at even 10 to 20% blends. So 5% is a very, very low blend. And there's a concerted effort over the last few years already to increase that blend limit, but it has stalled at the most recent semi-annual ASTM meeting. It was voted down, so they are still looking at resolving all the outstanding issues. Then I think after these two processes, the next process that we're going to see significant SAF volumes is the alcohol to jet technology. So we've already got ASTM approval for ethanol, isobutanol, and mixed alcohols. The feedstocks for alcohol production can vary quite substantially, so we can get ethanol from starches or sugars, cellulosic ethanol, ethanol from syngas fermentation, and this just describes a few of the processes. And the part where you take the alcohol and you convert it to jet, especially with a basic alcohol such as ethanol specifically, this is not a major technical obstacle. You look at the steps, you've got dehydration and oligomerization. So a lot of the companies such as Honeywell and so on have been around for decades, where they've been using these processes to produce chemicals. So I think UOP patented an ethanol to ethylene process already like 80 or 100 years ago. So these steps are established, and then we look at the hydrogenation and the fractionation. Those are also established refinery steps. So there's very little that's new. The new part is really the integration of these steps into a specific process to produce hydrocarbon fuels such as SAF. So we see there's already several companies offering ethanol to jet technologies for licensing. And then the first company at commercial scale, the LanzaJet Freedom Pines, Georgia, it's a first of its kind. I think the capacity is 40 million liters, and they're planning to have a 70% fraction. They were affected by the Hurricane Helene, but as far as I understand, they should deliver the first SAF volumes in October. So once this company is up and running, it will see rapid expansion of alcohol to jet. That's my projection. And I think there's at least 20 announcement of ethanol to jet facilities, and a lot of them are based on the LanzaJet technology, but there's a lot of the other ones. So this is a huge opportunity for a technology that is not that complicated and has already got a track record for individual steps. The biggest issue really with the alcohol to jet is which alcohols to use, because you've got conventional alcohols from crops such as corn and sugarcane, and then you've got the advanced ethanol. So if you use crop-based ethanol, this is relatively simple and it's cheap, and there's a lot of it available already, like 120 billion liters of crop-based ethanol is already out there. But under policies such as the ReFuelEU mandate, you cannot use any crop-based. In the US, you can use corn ethanol for producing for the alcohol to jet process. The problem is how to get it under or with more than 50% carbon intensity reduction, because otherwise the companies cannot actually earn the inflation reduction credits that demand a minimum reduction of 50%. So the newly approved 40B SAF breed may allow companies to earn or get greater than 50% reduction, and this will be mainly based on agriculture and farming practices, but it's not that easy. But if we then look at sugarcane ethanol to jet, this can already, based on CORSIA, achieve a 57% reduction in emissions. So while corn ethanol maybe have some difficulty, sugarcane ethanol has a significant opportunity. Then if we look at cellulosic ethanol to jet, based on CORSIA, this will only earn a 65% emission reduction based on agricultural residues. So there's not such a big difference between those two. But so when we look at the potential volumes from the alcohol to jet technology, what we see is all of those reports completely exclude crop-based ethanol, because the standards, the aviation sector standards, they say we're not interested in crop-based ethanol. We're only interested in advanced ethanol like the cellulosic ethanol. So in the EU, the UK, they don't want any of these. They only want ethanol from like advanced ethanol. But the problem is that for the most part, cellulosic ethanol is not commercial and widespread commercial availability is very low. Raízen in Brazil is probably the only fully successful company that is producing cellulosic ethanol from gas, and they have plans for building at least 5 facilities. They have investments from Shell, who has already got an offtake agreement for all of the sugarcane ethanol or cellulosic ethanol that they can produce. Praj in India is also a big company working towards commercializing cellulosic ethanol. But for us that have had a history in this field, we know that it's actually had limited success, and most facilities since way back in 2013, when the first one, the Beta Renewables plant, opened in Italy, most of those companies have failed. And even recently, the Clariant facility in Romania closed down. And the biggest issues were actually the high cost of production and the challenges with feedstock logistics. And if you look at techno-economic analyses, when you want to make SAF from cellulosic ethanol, the minimum selling price is more than double that of corn ethanol to jet. And those remain significant challenges. And just a few comments on the feedstock supply chain and logistics with agricultural residues. I can just mention, for example, if we bear in mind that residues are harvested from a few hundred farmers, and you have to have, as a refinery, individual contracts, and this is all harvested within a short period of time. You need large-scale storage, probably hundreds of thousands of bales. And if you look at some of the scales that we're talking about, I looked at some techno-economic analysis where if you wanted 220 million liter alcohol to jet facility, you are probably going to need more than 2 million large round bales. So just looking at the logistics of that, it's enormous. And the way that you store it, the quality is reduced during storage because there's microbial degradation, and that affects the yield. And from what I've heard is that was one of the things that affected the Clariant facility. If you don't get the yield, of course, the costs go up. So there are significant challenges with these residues that is not actually even related to the technology for making the ethanol. And a lot of companies are not looking at how to resolve this. I do know that under the SAF Grand Challenge and organizations such as the Idaho National Labs, they are actively looking at solving some of these problems. But these challenges are not sexy technology challenges, but will be very substantial in terms of making this work on a commercial level. So under the alcohol to jet, we do have the opportunity to potentially use crop-based ethanol to actually prove all these different technologies. And the other benefit with ethanol is that because it's a high density intermediate, if you can put it like that, it can be transported over long distances, which is already happening. So we can actually have large-scale facilities for aggregating ethanol in order to make large-scale alcohol-to-jet facilities. But the main challenge is for the advanced alcohols, the availability and the cost. And the US approach, where it's sort of feedstock agnostic, where they look at improving the carbon intensity score rather than excluding a crop-based ethanol completely. And I think what, in terms of sugarcane ethanol, what we can see is that it can give substantial emission reductions. And everywhere in the world where sugarcane is grown, all of these companies are very interested in producing SAF based on sugarcane ethanol because I would say it's a potentially cheap, low-hanging fruit SAF that that can be produced at a very low cost compared to cellulosic ethanol. Then just to switch to, I think, technologies that are going to take longer, the gasification and Fischer-Tropsch technology. As we know, a few months ago, the first commercial facility, Fulcrum Bioenergy, closed down. And this is really having, I think, a substantial impact on the commercialization of the technology. Very little information has been publicly available, but it seems that the problems were likely due to feedstock complexity. One of the reports said that there was a buildup of a cement-like substance meters deep inside the gasifier, and there was also formation of nitric acid, which corroded the metallurgy of the piping and so on. So feedstock challenges are huge, and in the case of when you hear this description, you think, okay, potentially there was tar formation because of the feedstock, and then the ash maybe was binding to the sides of the gasifier, and this was really substantial. The ash content in municipal solid waste, for example, is about 20%. So these feedstock challenges are really, really substantial and has to be resolved. And because of this closure, of course, now investors are more reluctant, and this represents a higher risk than what it was before. And investors are really saying, okay, we're going to wait for the first one to succeed before we're putting money into this. So while the gasification is challenging, but absolutely critical, because this is one of the few technologies that can access feedstocks such as municipal solid waste, forest and agricultural residues. And we know that these feedstocks are the most substantially available feedstocks that are available everywhere in the world. So we need these technologies to succeed. At the same time, the gasification pathways produce SAF with the lowest carbon intensity. And Fischer-Tropsch is fully commercial once you've got a clean syngas. That's been proven over decades. But in those facilities like Sasol, they used coal, which has a much very, very different chemistry to biomass, or they used natural gas, which is a lot easier. So the problem is with biomass is that there are significant issues, and therefore it's the part up to the Fischer-Tropsch, the production of the syngas. All of that coming before is the problem. Then also similar to HEFA in a way that you can either produce a low jet fraction or a high jet fraction. So once you've produced your Fischer-Tropsch hydrocarbons, what we call a straight run fraction, if you just do a distillation at that point, the straight run jet fraction will be less than 30%. So now you can take that and you can put it through with higher capex and investment. You can have a hydrocracking unit, and that's what a lot of these companies are doing. They produce diesel range molecules using a cobalt catalyst, and then they want to crack it into smaller fractions. So what you see in a lot of reports is that they're basing their estimates on even up to a 70% SAF fraction. But just bear in mind what I said. You now need a higher investment, and the more steps you have, the more expensive it becomes. So one of the research areas in this is to design new catalysts that can produce up to 70% jet fraction without all this cracking. So that's a sort of novel area of this technology. But if we look at gasification Fischer-Tropsch, the challenges have not changed. It's still the same. It's the high capital cost. It's the long construction period, as I mentioned earlier, at least 5 years. And if you look at this, I'm going to show this graph again later. These first three is Fischer-Tropsch, gasification Fischer-Tropsch from municipal solid waste, forest residues, and agricultural residues. And this is the comparison with alcohol to jet and with HEFA. And I'll show this full graph later on. So the feedstock characteristics still the main challenge. You get the tar formation, you get contaminants, the syngas cleanup is expensive. Because of the oxygen in the biomass, you get a very low hydrogen to carbon ratio. You have very low feedstock density, so transportation costs are expensive, and you have to build the facility closer to the feedstock, and you have all these supply chain challenges because these feedstocks haven't previously been used. So gasification is still a big challenge, but absolutely critical if we're going to be able to access feedstocks that are available in very large quantities. So switching to power to liquids, there's a huge reliance on power to liquids as providing a substantial volume of SAF. In the EU, the ReFuelEU mandate, power to liquids is supposed to deliver 50% of the mandate. So this is a very significant technology. Firstly, using carbon dioxide, which can either come directly from the air or from point source capture. Then using the reverse water gas shift reaction to produce carbon monoxide. And on the other hand, taking water and renewable electricity through electrolysis. And then you basically get your syngas, and you can use a Fischer-Tropsch synthesis process. Alternatively, you can use a methanol process and then a methanol to jet in order to produce SAF. So the dedicated mandate for eSAF in the EU is really driving the development of this technology. And under the EU mandate, they fuel suppliers in the EU will require about 600 million liters of eSAF by 2030. And it's likely that this target will not be achieved. A few months ago at a conference, I think Arcadia eFuels announced that they've reached final investment decision, but they estimated that it takes about 7 years for companies to get to actual production stage. And while there's been a lot of announcements of power to liquids companies, most of them are not at FID stage. And therefore, if you look at that 7-year time frame, it's going to be very difficult to get that. And while elements of this process is already commercial, so electrolysis of water is commercial, Fischer-Tropsch synthesis is commercial, but the CO2 capture is still in early stages. There's some commercial, but it needs to be proven fully. And then the part that's at a lower technology readiness level is really the reverse water gas shift reaction. And this is also one of the most expensive pathways. This is a graph that I'm also going to show later on that shows I think this is capex. The capex per liter of fuel, and this is power to liquids, and this is the HEFA facility. And the electrolyzer, for example, alone is about 25% of the capture. Then you've got the carbon capture technology itself that's got high capex. And then the cost of electricity is a huge component of the production cost. Then you also need sufficient and additional renewable energy for hydrogen production, because if it's not additional, it's not really benefiting the climate. And there's a lot of competition for this renewable energy, for heat, for electricity, for running electric vehicles. Everything is becoming electrified in order to reduce fossil fuel consumption. And so there's huge competition, and what we see is that droughts, for example, are affecting hydroelectric. And so overall, it's questionable whether we're going to have enough renewable energy in excess of decarbonizing all our electricity and heat. So, because power to liquids is actually an inefficient way to use electricity, if you just use it straight for charging a battery, it's about 6 times more efficient than e-fuel production. We also see a very high cost of direct air carbon capture as opposed to point source capture. As I mentioned, the reverse water gas shift reaction is still at a lower TRL level. And although separate steps are maybe commercial, the whole integrated pathway needs to be proven. So this is just a quick calculation from a McKinsey report on power to liquids, showing you that you need about 36 megawatt per hour for 1 ton of e-fuel. But if you use direct air capture, that in itself uses substantial electricity, and you get 2 types. The one is a high temperature direct air capture. I think that's like the carbon engineering. And so that would be the upper range of the electricity consumption. So for 50,000 tons of e-fuel, 60 million liters, you'll require about 1.1 terawatt hours of electricity, equivalent to more than 2,700 acres of solar PV. So although we see that significant emission reductions are possible, and that it's theoretically unlimited potential, because we don't need biomass feedstocks, and that's a huge advantage. You don't need arable land, but sufficient renewable electricity could be limiting, and the whole issue of intermittency, especially where you are going to rely just on solar. You have to now have extra capex for storage of electricity and so on. And if you are building solar PV in desert areas, you also have to look at the water demand for creating hydrogen, and desalination will obviously be additional capex and so on. So, but when you look at the prospects for long-term cost improvements based on cheaper renewable electricity, whereas, with other technologies, it's a high infrastructure cost. There's less opportunity for lowering cost. It's more incremental improvements. But a big part of the power to liquid cost lies in the price of the electricity. So if the price of electricity is reduced substantially, it has a more opportunity for reducing the production cost of power to liquids. And then you also have the methanol to jet as an alternative route, where you can, for example, produce the methanol and then have an aggregated large-scale methanol to jet facility elsewhere, although that has not yet been ASTM approved. And then I'm not going to go into detail on this because I think we are already been going a long time, but I'll briefly mention the direct thermochemical liquefaction pathways, which is fast pyrolysis, catalytic pyrolysis, and hydrothermal liquefaction. And again, this is one of the critical technologies that can use feedstocks such as forest residues and other wet feedstocks such as sewage sludge, food processing waste, etc. So it's far from, I think, commercial stage, but will be critical, I think, to access some of these feedstocks that other technologies can't access. So although production of biocrude is commercial based on fast pyrolysis, upgrading is still a challenge. There are some companies working in this space, such as Alder Renewables, but this technology pathway is not ASTM approved. There's significant research into SAF production from sewage sludge, and that's a huge opportunity for accessing wastes that no other technology can really use. And then there's also the opportunity of using the bio oils, the liquid intermediates for co-processing, particularly if you look at the issue of feedstock density, where you have to locate the facility close to the feedstocks, but that is not necessarily a suitable place to produce your finished fuels in terms of the downstream supply chain. So if you can aggregate to get economies of scale and have a large scale upgrading facility. So, but I think the other part of the report that I'm going to just briefly mention a bit is, I think that policy will be the critical driver for all SAF development. I've been talking about technology challenges, and I've been talking about feedstock challenges. But ultimately, policy is going to be the most critical factor. Scientists can solve technical issues. That's not the issue. The problem is that no matter what we do, it's going to be more expensive compared to conventional jet fuel for a very, very long time, and maybe even up till 2015. So the only way that this is going to happen and how we're going to see commercialization and scale up of these volumes is if we actually put the policies in place. And there was just this, for us who've been in this space for quite a long time, when policies in Europe and the USA came in, there was just this dramatic change in terms of the announcements of facilities and all of these things taking place. And in Europe, we've seen the stick approach, and in the US, we've seen the carrot approach to policy. Regardless, the policy is kind of moving the needle. One of the biggest issues, as I mentioned, is the large cost differential with conventional jet fuel. The current price of HEFA is still over $2,000 per ton, whereas depending obviously on crude oils, but conventional jet fuel is maybe $700 per ton. So we need to bridge that price gap through policy in order to get these technologies to become commercial. We're going to see a higher cost of producing SAF for a long, long, long time. We have limited availability of feedstocks. There's limited investment. I think companies will tell you there's a lot of funding out there, but the problem is it's still, there's a very, very high risk because these technologies have not been proven yet. And aviation also has to compete with road transport for feedstocks and so on. But the reality is that you look at all the reports and the cost difference with conventional jet fuel can remain and will probably remain until 2050 for most of these pathways. And then I just want to quickly show you two slides that with production costs. So this is from, and you can access this online at the ICAO website. It's work that's been done at Washington State University by Professor Michael Wolcott and Kristen Brandt. And ICAO has compiled this into what they call the SAF rules of thumb, and it shows you the minimum selling price based on a net present value of 0 in order just to compare, with orange being pioneer facilities. The first type facilities are very expensive, whereas the nth facility, 10 or 20 facilities later, the cost production. power to liquids, and it just shows you the advantage that HEFA has and that alcohol to jet from crops has. And then, and you'll be able to get the slides afterwards so you can look at this in greater detail. And here's some of the capital cost. And yet you'll see the capital cost dollars per liter for gasification. And here is the capital cost for alcohol to jet and HEFA. So some of these technologies have really, really substantial challenges in order to become commercial. And without policy, SAF development will be limited. It just can't happen. So what we need are policies that are stable over a long period of time, 10 to 20 years. So in the EU, we see the mandate, and that's maybe not a very policy that not everyone is happy with, the stick approach, but at least it's there over the next decade. So there's a certainty. In the US, we've got the carrot approach, but the blender's tax credit was 2 years, and the producer tax credit is 3 years. And the political uncertainty means that there's no stability for the policy. So we do need to bridge that high price gap. We need to address the high capital cost to make it easier to build these facilities. We need to de-risk investment to allow technologies to become commercial and scale up. Because we need to increase production and availability. If you don't have the first facilities operating, you will not see the decrease in production cost and the scale up that we need, because you have to start small and scale up gradually. Otherwise, the companies could fail. And of course, everything has to be done within the broader issue of sustainability and emission reductions. It's not just the volume of the SAF, it's the emission reductions and the fact that it's all sustainable. And yeah, I'll just show you this map that you must have seen at various venues and conferences to show you some of the developments around the world. But again, a country might say, okay, we want 10% by 2030, but that is just an ambition until there are policies put in place to actually achieve that. So in conclusion, HEFA is fully commercial and will continue to be the main technology. With limited investment, if we have the policy in place to direct that shift, we can divert some of the renewable diesel to SAF, but we need to also expand the HEFA feedstocks that give us a very low carbon intensity HEFA while we have this commercial technology. But we do need all technologies to become commercial because many of them can access feedstocks that no other technology can actually access. We have to realize that it takes time and that expectations can be very unrealistic, and all of this pressure to build these massive facilities can just be a recipe for disaster. I don't think a technology that's unproven can go and build a facility that's going to produce 200, 300, 400 million liters. I think those are in danger of failing because it has to be shown at a smaller scale. And we've seen that with companies like Kior in the past. But without the policy drivers, this is not going to happen. So thank you very much. And here I've just put the link for that report and happy to take any questions.
Thank you very much, Susan. We do have a lot of questions. I think you covered many of them, but some of the issues that have been brought up, I would just emphasize the last point and I would use the word stress testing. There's such an urgency to show the technology works that inadequate stress testing in the scale up is occurring. And so scale up is people are trying to scale up too fast, as you said, without the adequate stress testing at the prior scale. where the cost of doing it is much cheaper, much lower. Another thing that I don't think anybody brought up, but I'll bring up as a first question, is the import in many of these technologies of having an adequate and cost effective in the context of the process source of hydrogen. That I haven't heard hydrogen mentioned here, but many of these technologies are requiring hydrogen, and that seems a central premise. Do you have anything to say about the green hydrogen or the availability of hydrogen, the role of hydrogen in these processes?
Of course, yeah. I mean, technologies such as pyrolysis have huge hydrogen demand, and ultimately, we want that hydrogen to also come from renewable electricity. So that is huge, and companies are looking at taking the natural gas, hydrogen, and then capturing the carbon to make blue hydrogen. But then, that might not have good carbon intensity, and NGOs say, well, that's going to perpetuate the use of the natural gas. So it all goes back then again to the renewable electricity for the green hydrogen.
Thank you. I would encourage attendees to upvote questions because there's so many of them. I could help to sort of get their importance organized better if people would upvote them. There's been a few that have been upvoted, and I want to thank Paul Bryan for lots of his comments and questions in the Q&A. The Q&A itself will not be available, will not be posted. So if you're interested in that, you should copy and paste it somewhere during the webinar. One of the first questions, and Paul's addressed this also, is the indirect land use concerns of some of the feedstocks, and particularly, I think, with respect to vegetable oil, since it does have that dual food use, and the fact that, if there's competition for this feedstock, the price will escalate, and then many people will go hungry or, suffer the consequences in the food supply. So that's one I would like your comments on the ILEC concerns, particularly with vegetable oil. Obviously, captive waste materials are good. You talked about that, but they're finite, they're limited. So,
well, the first thing about I think vegetable oils like crops is that there's a food and fuel component, and I've seen the FAO also saying that type of thing. We want to just exclude these because of the oil being diverted to biofuels. But if you look at, say, soybean oil, that's only 20% of the seed. You get like a 50% protein meal. So, I shake my head when I think, okay, you've got a poor country in Africa who has to import all their oil to make transportation fuel. You want to go and plant jatropha there that has a toxic protein meal. Why don't you just expand crops that can both feed as well as give energy security to those countries? I don't know if it always makes sense. But the other thing in terms of ILUC, so it's important when we calculate the carbon intensity that ILUC gets taken into account, and the CORSIA defaults do take that into account. Whereas, for example, under the EU RED, there is no ILUC. So it's important that we look at the life cycle assessment and whether ILUC is taken into account, and that the policy should drive carbon intensity. I think that's really, really important, because if you add ILUC, a lot of these crops will not really give you an emission reduction that's worthwhile. But at the moment, we're just pricing the volume rather than pricing the carbon intensity reduction. So I think that's something important, not just say, okay, it's so much, but per ton of fuel, but there should be a difference between a fuel that gives an 80% reduction and a fuel that gives a 10% reduction. So like if you'll also look at CORSIA, palm oil can get you a 10% reduction or is worse. So I think that's for me, rather be feedstock agnostic and put in place the policy that drives the lowest carbon intensity. And put limits maybe on feedstocks, like the California Low Carbon Fuel Standard just decided to limit fuels coming in, the crop-based renewable diesel to a 20% limit. So that makes sense, but don't just ban a feedstock completely and then rely on a technology that's not commercial. You know, we need to have a pragmatic approach, I think.
Yeah, so back to policy. There was also questions about the about a couple of the routes that people are quite interested. So I think you talked about these already, but Fischer-Tropsch is a big interest area. Paul comments that it remains too expensive. Ethanol to jet is viable, and we could, I mean, that's in progress. It's technically viable. Is it cost viable? Is it, you know, how widely can it be deployed? Remains a question. But the other big interest is in the biomass to methanol and then methanol to jet. Can you say more about that and where that's occurring? Is that more robust? I mean, it seems to me you've got I can't even say it, but you've got to do a little more work to take methanol to a large molecule than you do ethanol, but it's the same kind of approach, same issues.
Yeah, I think the feedstock. I've been thinking of that quite a lot. Is there is Fischer-Tropsch or methanol a better route? From a feedstock point of view, you've got similar challenge. You still need to do a gasification. Enerchem here in Canada, they operated a demo facility based on municipal solid waste for methanol production, but they closed that down, and they're currently building a large-scale gasification to methanol facility in Quebec. And yes, there is a potential, but from the methanol production, you need very, very high pressures. I think something like 50 megapascals. The methanol to jet it's similar to the ethanol to jet. ExxonMobil, the Mobil methanol to gasoline process was done like decades ago. So now they can modify the process to produce longer chain jet molecules. So I don't expect those technical issues to be huge either. There was a paper published, I think, just a few months ago that compared the energy efficiency between the Fischer-Tropsch and the methanol to jet pathway. And I think it depends whether, if you just want to produce jet, I think the Fischer-Tropsch is better. But if you just look at the total volume of product, then maybe the other one will be better. But it's not that clear to me which one is better.
There's sort of a one of the last questions we have, which hasn't been, it's been just a little bit upvoted, but I think it pertains across the technologies, and it mentions the analysis in the report is mostly qualitative in terms of the economics and GHG emissions. And the question is IEA Bioenergy, I'll say in this case, Task 39, going to do TEA and LCA to quantify the economics and carbon intensities of these different pathways for specific regions and countries? And I will just sort of say that please provide the data to allow us to do this. It remains elusive to get full data sets that are sort of peer reviewed or vetted. Generally, this information is behind the curtain and we don't have very good access to it, but you could maybe say more, Susan.
Well, yeah, the scope of the report was not to actually go into depth on that. So I either used the Corsair defaults or I used for the techno-economics the work done at Washington State University, which is really comprehensive. But that type of analysis has never been done in these reports, and this is also the last report that I will be doing. I think. Jim, your colleagues at NREL, I think, will be taking the lead on this report for Task 39 in the future.
And the same issues pertain. Jack?
So Jim, I just want to pick up. So Laura's put some really interesting information on the iLook on the chat. So thanks a lot, Laura. So I mean, I think iLook is very complicated. I know several of the people online have been at meetings, and there's real experts looking at iLook, and there's no consensus what we mean by iLook. Also, if I look at with our forestry background, there's a bigger time frame as compared to agricultural residues, which you tend to look at annually. Forestry, you tend to look over decades. So I think Laura's contribution is great. I mean, my sense just now. So Jim, quite a lot of us have been working on cellulosic ethanol for most of my career, and we can technically do it, but economics are really, really challenging. I think, as Susan covered, going from lipid to jet, we can do it. And basically, it's not a technical challenge. It's the feedstock. How do we get a cheaper feedstock? How do we make it more sustainable? So I think the difference between cellulosic ethanol and lipid to jet is that we can do it. So it can be done. So I think also what I find is the oil sector is a key player. I think Susan touched on this. I mean, where do we get our transportation fuels from? It's basically from the oil sector. So Susan and I have a constant discussion with regard to what will follow lipid to jet. So I'm a big proponent of co-processing, as Susan knows. So if I look at co-processing, you can use vast amounts of lipids in co-processing very quickly. And I think that will be a key player. Also, we make a distinction between the lipids. There's basically waste lipids, like fats, oils, and greases, use cooking oil, and virgin lipids. So if you look at waste lipids, basically the indirect land use or any of the carbon shouldn't be an issue, but there's a limited availability of waste lipids. However, there's more and more collection of waste lipids. So look at what's happened is people are actually collecting more of that material. I think what comes through in the report is that we're probably all going to have to pay a bit more for flying because fuel is a major component of flying. I think the only way that aviation will decarbonize, we can use green electricity for short flights. We can use green hydrogen for maybe middle-sized flights, but the plane's mostly going to be full of hydrogen. So the only real option is going to be biojet or sustainable aviation fuel if we're going to fly from, say, Canada to Europe or to Asia. So I think it's really interesting because as Susan covered today, we need all of the above to work. So we use huge amounts of jet fuel. And so it's really what we're trying to do is I think the lipid to jet will grow, as Susan covered. I also think that what will happen is we need these other technologies to work as well. So I think really what comes through in the report is a review of all the reports. So I think many of the people on the call are technology providers, and we want them all to succeed because we need all of these pathways to work. So Susan, you got your hand up.
Yeah, I just wanted to, just pertaining to Laura Lanza's comment, I apologize because it did sound incorrect what I said. I just want to read to people that are still on the call. With regards to iLook, I said that EU, they don't actually consider iLook. And as Laura explains, that they do consider iLook, but basically they say, as far as I understand, that where crops or feedstocks are considered a high iLook risk, they are actually capped or even excluded. But what I meant is that the carbon intensity is not calculated with an ILUC value included, such as CORSIA. And I think the Canada Clean Fuel Standard has the same approach as the EU in that respect. So excluding or capping low risk or high risk feedstocks. Sorry about that. Sorry, Laura, if I
So
created
Jim,
confusion there.
I've add to Susan, I mean, I think both a stick and a carrot approach. I mean, I think the EU, I think the UK, for example, has got a stick and a carrot approach. So I think you do need, as Susan covered eloquently, you need that policy driver, because just now it's more expensive. So I think what's interesting, do you go with a mandate? Because one of the problems we had with cellulosic ethanol is the US EPA mandated cellulosic ethanol. The problem was we couldn't make cellulosic ethanol, so the mandate didn't work. Whereas I think the mandate might work some areas, because we can actually make jet via the HEFA route. So I think what's really interesting just now is what policies do we use? And as I covered in the introduction, with us being located in British Columbia, it's pretty good because we have a carbon tax, we have a low carbon fuel standard, so the policy environment is pretty good. We're a good supplier of feedstock, so many of the lipids go through the Port of Vancouver, so we can access lipids. We have lots of biomass. We're a major exporter of wood pellets that could be used, so good place to be, other than the fact that this, as Susan covered, it's going to be expensive to make Biojet, and also the some of the technologies are capital intensive. So you're taking a big risk. You got to convince the bank to give you the money to try and make this work. And the problem is jet fuel is relatively cheap, and we can't forgive the tax because a lot of the jet fuel is not taxed. So I think the policy environment is challenging.
Very challenging. Well, there was a number of questions about co-processing and you talked about the high capital costs of a lot of these systems, and co-processing offers an opportunity to utilize, existing capital, which would enable scale up to happen quickly. But, achieving the renewable content levels in the fuel remains a challenge. And could you say more about that? I mean, if you co-process 20% material, you're going to have a hard time getting 20% in your jet fuel fraction. Could you say more about that, Susan?
I think it depends where you co-process. Obviously, if you think of say lipids, you have about 11% oxygen. That oxygen is removed in three ways: through water, through carbon dioxide, and through carbon monoxide. And the carbon monoxide and carbon dioxide, that will come from the renewable content. That's kind of, but if it's in say a diesel hydrotreater, your yield is pretty good. It's when it comes to the FCC that you might have some bigger problems, because there's a lot of coking and the coke gets burnt. So it's a far more complex system. But you can go very high in terms of co-processing. And of course, then if you try to co-process fast pyrolysis bio-oils, it's got up to 45% oxygen. So that's really the issue that lowers the yield. But it is very challenging.
Thank you. There was questions about microbial-based oils, and I would say it's really a cost issue, right? Again, is that you'll concur with that?
Yeah. I mean, if you look at algae, which is there's a lot of interest, but even if you just go and look at the US billion-ton report, the most recent one, oils from algae will be the most expensive of all of them. And it's part of that is just because of the way it's grown. It's in water. It has to be extracted, and that's one of the most expensive parts. How do you actually extract it from a very, very dilute type of basis? And then there's also the whole issue of producing, say, smaller fatty acids through biochemical processes. But every time you are trying to do something with the microbe, it is more challenging because of yields and separation. There's, there are challenges. The biochemical routes are generally more expensive and better for making chemicals, biochemicals. I mean, that's why Amyris, even though they can make SAF, actually they make far, far more money by making medical products and supplements,
without having to scale up hugely.
And
Nearly as
then
much.
without having to remove the oxygen, because biochemical processes have oxygenated molecules. But if you can use it for a supplement, you don't have to then worry about removing all that oxygen. And you can if you look at algal systems, you can produce multiple products. You can do spirulina. The fuel is the lowest value product out of all of those.
Yeah. So maybe a concluding, I see we're getting close to time, or maybe slightly over. There was one question I think that summarizes well. What is your best estimate for what we'll see in production this year for SAF and in, say, 2050? If you were, you're a prognosticator.
If anybody knows what's going to happen in 2050, good luck. Well, I think IATA has already done estimates for 2024 in terms of SAF volumes, and it was I don't know, anything from 1 billion liters to maybe 1.8 billion liters. But again, it's so hard to distinguish the real information from just the really positive, like we're going to do 70% or 90% SAF, when there's just a lot of not misinformation, but there's a lot of sales pitches rather than actual information. And as someone said at the conference where I was last week, I can tell you how much, but I can't tell you when. You can either say when or how much, but you can't say both at the same time.
Yeah, we would think in the U.S. we're being hammered by the impacts of human driven, to a large extent, climate change, and we see the costs. I just heard a report today that the cost of one of these hurricanes is like the total is half the total investment of the IRA in green technology. So we're bailing the boat, but the hole's getting bigger and it's getting harder to bail the boat. We really do need the policy lever to reflect the urgency of the situation and to help drive these technologies as we really desperately need them. So I don't know how much longer we get to go. If I can go through more questions, I will.
So Jim, I think we're supposed to round up. I can see people are leaving now. So I just want to,
okay,
on behalf of Susan and I, thanks a lot for moderating. You made just as much sense as you always do. So again, Jim, I'm really grateful for you for doing it, and also thank our Task 39 colleagues for allowing us to do this work. So, and thanks to our colleagues in Italy for organizing the webinar.
And thanks everybody for attending.
So I think that's it with the time, but
all right, well, thank you again, everyone. We're going to close the webinar now.